So thank you everyone for joining. So for this presentation, I'll be talking about some results that were obtained through the Frontier Development Lab during 2022. And if you're not familiar with the FDL or Frontier Development Lab, it's basically a yearly multidisciplinary effort that's pushing for the development and application of novel AI tools to tackle challenges in science, including, like in this case, heliophysics. And more specifically, this presentation will focus on how we can use AI and 2D images to try to generate a 3D model of the sun's atmosphere. And you can see on the right, basically, the members that were part of this team. So all the work is a collaboration between all of them, whether they're heliophysicists or AI experts. So let's start with a bit of background. The sun, of course, it has a significant impact on our daily lives, but most importantly also on our technology. For example, if we look at the UV light that the sun emits, it is absorbed by Earth's atmosphere, and it degrades the orbits of satellites as an effect. Because part of that EUV emission is absorbed by Earth's atmosphere. And we have an example here of the Starlink satellites that unfortunately burned down in Earth's atmosphere following space weather events. So in addition, the sun is the only star in the universe that we can fully resolve, which is very important in terms of using the sun as a template for other stars. And stuff like the EUV emissions are also an important factor in the evolution of atmospheres of planets. So if you want to connect to other stars that may be hosting planets, the knowledge that we can extract from it is pretty important. So ideally, we'd like to have a complete image of the 3D sun to really understand the dynamics that operate. So from eruptive events to space weather in the solar system, so that we can also forecast EUV radiation to protect our assets in space, to relate the sun to other stars, and also generalize the knowledge of the SunREF system to other host stars. But there is a challenge. EUV observing instruments are limited in terms of the numbers, but also in terms of the perspectives that they can provide. So let's look at the schematic. We have basically Earth's orbit, and the plane that it traces around the sun is what we'll refer to as the ecliptic. We have some instruments that observe in EUV. So we have the Solar Dynamics Observatory that's basically following Earth as it goes around the sun, and it provides us a perspective of the sun, but all it can give us is a 2D image with one perspective. There are other satellites that are going around as well. So this is a perspective that I'm giving that's mainly true from 2010 to 2014, but I'll mention later on how we can generalize for something that's more recent. But we have the stereo satellites that basically have orbits that are falling behind and going ahead of Earth's orbit, allowing us to get different perspectives of the sun. So stereo behind and stereo ahead. But still, that's only 3 perspectives, which is not a whole lot. And it's all from the ecliptic, as you can see. So we don't have an instrument that's really looking at the poles, for example. So we wanted to address the question, how can we observe the sun from any perspective? So not just from the ones that we have currently with, for example, SDO and stereo, which are all limited to the ecliptic. So let's go back to our little situation here. One solution, easy enough, is just send more satellites. That's just $1 billion each. NASA's deep pockets, they can for sure afford it. It's really not the solution we like to aim for. The solution that we're going to propose actually is to go for virtual instruments. So something that is not really existing and that will cost you nothing in comparison to a satellite. And if we have virtual instruments, we're no longer tied to the ecliptic. We could try to go for non-ecliptic orbits as well, or look from completely new perspectives. And this strategy is something that we'll try to tackle using AI. So we'll use AI to develop virtual instruments that are going around the sun. So that was basically the challenges that we wanted to tackle for the Frontier Development Lab with this. So we wanted to make 3D maps of a complete instantaneous view of the sun. And it's what I'll focus on for a presentation. We did have another objective, which is focusing on EUV irradiance, but that's a whole talk for itself. So we'll just focus on the first part for this. So let's just quickly mention the data that we'll be using. So we're using here EUV images of the sun from SDO and stereo, like I showed before, and we'll focus mainly on 4 wavelengths, which are basically wavelengths that are shared between the different instruments. Although AIA can measure more than that, but we'll just use those. So 171, 193, 211, and 304. And as you can see, stereo has basically equivalence, except for 211, which is 284, but we have a little strategy here to try and compensate for this, which is also related to AI. And I'll mention this very quickly because this, again, could be a whole talk in itself, but so with that, we can homogenize data captured from the different instruments. So SDO and stereo, we're going to use AI tool. It's called ITI, which stands for Instrument-to-Instrument Translation, which was developed by Robert Yerlin from the University of Graz, which is basically a generative adversarial neural network that was trained to take images that were captured by stereo and then transform them to make them look as though they were observed by SDO AIA. So basically, the neural network is presented stereo images, which are then transformed, and then it has to learn how to distinguish between a fake IA image and a real IA image. And at some point, it is no longer capable of distinguishing between stereo images that have been transformed into AIA images and real AIA images. So this is a tool that we're using just so we have a homogeneous data set, because otherwise the different instruments have different calibrations or the wavelengths might be slightly different. So for example, if I go back, how we go from 211 on one instrument and 284 to one instrument is thanks to ITI. We're going to transform the 284 into a 211 image using AI just to compensate for the fact that we otherwise don't really have a way of transforming it. But yeah, like I said, I'd love to tell you more about this, but this is a whole talk in itself. But just to keep in mind, we want to homogenize data sets because otherwise you can get situations like, so this is an example of the current state of the art in terms of making maps of the full sun. It's something that we call a synchronic map. And it combines images from stereo and SDO together. So 3 instruments all in one image. And it shows you the full sun in some reprojection. And as you can see, you can clearly tell where one instrument ends and one instrument begins, because in this case, they were not homogenized. While this is useful and really interesting, such maps, they have issues in terms of reprojection effects, especially as we get towards the poles in the limb. As you can see, it's really hard to tell any detail as you get close to the top and the bottom of the image, which would correspond to the pole, because we don't have a direct view of that. And then, yeah, you can tell when there's instruments changing from one to the other. And the big challenge, which we also wanted to address, is those images are just 2D. They're basically measuring something that's 3D, but it's projecting everything in 2D. So it's like a flat surface, which is interesting, but we ideally like to have like a really full 3D model. So we're going to step to AI to try to address this need. And the tool that we're going to be using is something that we call neural radiance fields, which are extremely popular in AI. And they're used basically to take 2D images of a scene or of an object or something and try to generate a 3D model out of it. So to explain, I'll just play this very brief video from NVIDIA. This was an example of their neural radiance field, or NERF. And as you'll see, we'll have multiple images taken. Oops, let me click this here. We'll have multiple images taken from a person at different angles. And then this is fed to a neural network that allows you then to generate a 3D model of that person. And you're able to go around it as though you had images, but you don't. Basically, the neural network has learned from the images and is interpolating at the appropriate positions what the view of that object would be. And it's quite interesting. But these methods, they were developed for example, in this case, a person, which is you get light that's being reflected off of that person. If you think of the sun, the physics are very different. We're not dealing with air. We're not dealing with objects that reflect light. We're dealing with an optically thin plasma, which will partially absorb and emit light within its atmosphere. So it's a lot more complex. So in terms of describing neural radiance field, I'll describe it from the perspective of how we had to modify it to make it work for a physical object like the sun. So I'll just replay the video again quickly so you just get the idea in your mind. But it is all about taking pictures from different perspectives. And you can think in our case of the different satellites around the sun. These are like the different pictures that we have access to, and how we'll use this to then make a 3D model of the sun. And, yeah. So let's go. This is the model. So we call it SunREF because it's a NERF of the sun. It's not very original. But the idea here is we can look on the right and I'll mention the different steps. So we have satellites, like we're seeing here with this miniature SDO, and it's taking images of the sun in EUV. What the neural network is doing is it's thinking that we have a 3D model of the sun, which is, for example, represented here in a box, which has a size of approximately 1.3 solar radii. Well, that would be like a radius, so a diameter of 2.6. So we have basically in there a 3D model of the sun, and we're going to be tracing light rays. So the ray starts from the observer, which is a satellite. It goes through the pixels of the image, and it goes to our 3D model. And as we get in the 3D model, we'll be sampling points along the light ray. And for each of those sample points, basically we define a position and also a time, because we're not limited to just using images on one instantaneous time. We can actually use data that's time dependent, which is useful in the case of the sun because the sun has a strong time dependence. It's very dynamic. So we're going to be tracing light rays and defining a bunch of sample points that are basically within the volume. And this is what's going to serve as the input data for the neural network. So as you can see here for step 2, basically what we're providing as information is the X, Y, Z, and T components of the different sample points. Then it goes into a neural network, which is all fully connected. And what it outputs is, rather than providing a RGB color scheme and a density, which is what the a classic neural radiance field would do, here we're actually going to estimate a absorption coefficient and emission coefficient, because we want to connect this to radiative transfer, or at least some basic form of it. So for every position and time, we're estimating a absorption and emission coefficient. And you get something like you're seeing at the bottom, where you have profiles for along the sample points of what the emission and absorption coefficients are. And then we integrate this and go back to a 2D image. So basically for every pixel, we have a light ray going through it. And at the end, we're recovering a pixel again. And then we can compare the image we've reconstructed with the original image that we started from. And that's the general idea. So the neural network is basically developing a 3D model of the solar atmosphere. And what it's using as comparison afterwards is that it tries to regenerate 2D images like what the satellites have observed. And then we can compare if the 2D images make sense or not. Something to mention is that the light rays that we're tracing, if they hit the surface of the sun, we make the light rays stop because the surface is optically thick. And we don't want to try to start going inside the sun because we really don't know what we're dealing with. So basically, we're just going to try to recover the atmosphere. So that's the general idea. I know I went fast, but hopefully it kind of makes sense. So just to show some examples, let's look at some results. And we're going to start with the validation. How do we validate a method like this? Well, we start with a numerical simulation. So we're using a numerical simulation of the EUV sun that was generated by Predictive Science. And basically what they provided us is 256 viewpoints. So as if they had 256 satellites around the sun observing it, which is what you're seeing on the left. The points are showing you like the different perspectives of where the observers or satellites are located around the sun. What we did was to try to recreate a realistic situation. We only extracted the points that were in the ecliptic plane. So approximately plus or minus 7 degrees in terms of latitude. So which amounts to only 32 viewpoints around the sun. So not a lot in comparison to the 256 that are there. And the question that we want to address is, if we train only using those ecliptic images, are we able to recover non-ecliptic views? Because that'd be very interesting. That means we could potentially look at the poles despite only learning from ecliptic images. So that's what we're going to do. We're only going to feed ecliptic images to the neural network, training on that. And as a validation process, we're going to try to see if we're able to recover non-ecliptic views. So here's an example of that. So what you're seeing here is the different points represent the different viewpoints that were on the previous image. So there's 256 of them. So we have the x-axis is showing you the longitude, and the y-axis is showing you the latitude. And the red dash line is showing you the plus or minus 7 degrees of latitude that we're using for the training. So basically anything that's between the two red dash lines were part of the training. So don't focus on those values too much. We computed some metrics just to check how they're performing, but really what matters is what's outside of it. And we have some PSNR and cell similarity index, two measures that are used basically to try and assess performance. So the higher value we get with PNSNR, the better the performance. And for SSIM, the closer you are to 1, the better the performance. And the thing that's interesting is, regardless of the longitude and latitude of the viewpoints, despite learning only from ecliptic images, the performance everywhere is still really good. So in general, it appears as though the neural network is capable of recovering fairly well non-ecliptic viewpoints, despite learning only from ecliptic viewpoints. And I know this is just showing metrics, but we can look at images to get a sense of it more. So let's look here. The middle row is the ground truth. So that's the simulation. The top is the baseline, which is basically synchronic maps that were reprojected onto a sphere. So they're created by just stitching images together, which introduces, unfortunately, projection effects and artifacts, and loses all 3D information about the atmosphere. So it's basically just a 2D image mapped onto a sphere. And then at the bottom, we have the SunREF reconstruction. So that's the 3D model reconstruction that we get using the neural network. And if you compare with the ground truth, just by, I know it's not very detailed of an approach, but you can see that in general, as even for different latitudes. So if you get from basically ecliptic latitudes all the way to latitudes that are closer to the poles, there's a pretty good agreement between the reconstruction that we have with the neural network versus what was in the simulation. So it seems like, again, there might be the possibility of recovering non-ecliptic viewpoints, despite only learning from ecliptic viewpoints. And here we can look at, for example, measurements of errors that we have in the middle row, and they're mostly associated with the limb or some of the more dynamic features like active regions. And then we made some uncertainty estimations. Those were done using ensembles of NERFs. So we have multiple versions of NERFs trained, and we just compared them to get use that ensemble to get an estimate of uncertainty. So that's an example that we get with the simulation data. But just for the sake of time, let's move on to some examples of applications to actual satellite observations, which is ultimately the goal. So we're going to try to use this again with our friends Stereo and SDO. These are going to be the satellites we'll be using. So 3 viewpoints, but we're going to be using them at different times as well. So you could think of it as more viewpoints because of that as the satellites move, and that time component, we can use that information as well. So let's look at this. This is an example of a 3D model of a sun that we generated using a SunREF. So it allows you to go anywhere, including the poles. And as you can see here, we'll see filament eruption right here. So there was that in the data, and it somehow learned to replicate it, which is pretty interesting. So something to keep in mind is that, for example, if you learn from images within a time sequence, you can only make a 3D model of the sun within that time sequence. Don't expect it to be able to extrapolate beyond that time sequence, because it no longer has images that it, or information that it has access to. So, but this is an example of a 3D model that we can generate, that we can spin, move around, and don't think of this as just 2D images. Now you have access to a 3D model of the solar atmosphere as well. So you could technically have height information and things like that. We can go back to the synchronic maps that I mentioned in the beginning. Again, we have the baseline on the left, which is how it's typically generated. And on the right, you have an example of a synchronic map that we could generate using our SunREF model. And it no longer has those weird artifacts. It has much less projection effects as well. But the thing that's really interesting about it is that it looks like with this, we can have a look at what the poles might look like. So for example, here from Stereo and SDO images, we're able to make an image of one of the poles, and potentially, I mean, don't take this as take this with a grain of salt. Of course, we don't have an image to compare against for this, but this is just like kind of an inference of what it could look like based on learning from ecliptic perspectives. And if, for example, here we did a test where we looked at coronal hole boundaries that were estimated using the 2D images on the left. So that's the boundaries that you get in blue. And then if we use our reconstruction of what an image of the pole looks like, we see that we were finding different boundaries for coronal hole the coronal holes. polar coronal hole. So slightly different because we have access to a different perspective. And most of the examples I've shown are at 193 wavelength, but we can actually do it, like I said, for 4 wavelengths in this case, 171, 211, and 304. And we can see the polar coronal hole in all of those, which is interesting. But again, take this with a grain of salt until we get a satellite mission that's actually looking at the poles directly in EUV. This is just an inference. And again, we can compare this to other methods, like if we take synchronic maps again and reproject them, these are the kinds of models you would get from the solar atmosphere, but they're just 2D projections. But now we have access to full 3D information and with the SunREFs, which is interesting. And we can use, again, our ensemble approach if we want to use it kind of as an uncertainty estimation in a sense. But again, because we don't have a ground truth, it's hard to really say anything. What's interesting about it is that with this kind of perspective, it allows us to view things kind of differently. Like in this case with segmentation, for example. So let's look here at an image of the sun that we have. It's showing you an image. I think this one was maybe captured by stereo. Yeah, it's stereo. Okay. Let's trace a red line at a specific longitude and rotate the sun so that this longitude ends up being on the side of the image, which is something we can do with our SunREF model. And now let's look at the emission that we have in the SunREF in 3D because we have access to that information. And that's what you get in the slice. There's stuff that's going out basically radially. So this is emission as a function of height. And what's interesting about it is that if you integrate radially that emission, you can get a total radial emission profile, which is what you get on the right. And as you can see, when you hit something like an active region, which is close to the equator, you get the most emission. There's like a spike there. But as you get, for example, closer to where this blue line, there's a coronal hole, and you can see a dip in our emission profiles, which allows us in a way to make the whole problem of identifying coronal hole boundaries. There's a lot of methods that have been developed for it, a lot of it also using AI. But this looks like a new way of trying to assess that by looking, for example, at those emission profiles. Once we see things going down, this could be how we define, like, hey, this could be a coronal hole boundary. It's just something that we noticed and thought was pretty interesting. And same thing, we can see a dip somewhere where there seems to be a filament. So that, again, novel perspectives that we're kind of getting with this kind of approach. And speaking of filaments, well, here we have an example of a filament eruption. These are not observations, by the way. This is a reconstruction of observations using our model. And it seems to capture that filament eruption, but not just in intensity. We have access to more. We have access, because this is a 3D model, we have access to height information. So we're able to estimate at what height some of the emission is coming from. And also, we're able to estimate, for example, absorption, which we can use maybe as a proxy for stuff like density. And we're able to see, for example, if we look in the middle, where there's flare ribbons associated with the eruption, they're associated with a height that's close to the solar surface, which is kind of what we expect. So it seems that it captures some of that behavior fairly well, although it's still not the most physically detailed kind of model, but it's just interesting to see these kinds of things. And I guess last couple of examples, and then I'll stop. We tried reconstructing the solar orbiter perspective. So we trained a SunREF using stereo and SDO perspectives only. So basically data from those two instruments, and we try reconstructing what the solar orbiter perspective is. And this is what you're seeing with the bottom row. We have on the left solar orbiter, and on the right, we have our reconstruction of the solar orbiter perspective. Keep in mind that the colors don't really match because we didn't do some sort of instrument-to-instrument translation in this case, because the tool does not allow for that. But if we do that, hopefully we'll get the color to match better. But it's just, again, just an idea that we can see that some of the features appear at the right positions. And we also are working on trying to estimate density and temperature. So not just emission absorption, but with radium transfer principles, we're able to make 3D models of density and temperature for the plasma, which is interesting. But for that, it's in progress, so I don't have much to share. I'll head with this video. It's basically showing you this virtual instrument of ours flying across the solar system and looking at the sun from new perspectives, having learned from stereo and SDO images, allowing us to get closer and further, allowing us to fly over the poles and regions that we've never observed really. So this is just an example of the kind of things that AI enables us to do in terms of enhancing observational capabilities that we have access to. And again, we can do it in multiple wavelengths if we feel like it. Yeah, so I'll hand with this slide. So our SunREF allows us to make 3D representations of the sun in EUV. It enhances the observational capabilities of using virtual instruments and allows us to get novel perspectives. And we have something that we're working on as well to try to combine it with a neural network to get estimates of solar radiance from any perspective. So I'll end it here. Thank you.
Thank you. Any questions? Feel free to pop in. For some of you, it's midnight, right?
Hi, we're here at the University of Newcastle. We have a question.
Oh, I was going to ask a question. Okay, thanks. A really interesting talk. I was wondering, the models that you showed us using the satellite input, are those trained on the data from the predictive science model, and therefore is it essentially that your reconstructions of emissivity and so on are only as good as the physics that's in the predictive science model? Essentially, do I understand that right?
So those models were not trained on predictive science data. They were trained directly on observations. So the first examples that I showed in terms of validation we're using predictive science, but all the examples using after that SDO and stereo, those were trained directly on images. So all we do is provide SDO and stereo images to the neural network, and it learns from those perspectives, and it then tries to generate a 3D model based on that.
How are the predictive science models created or calculated? What physics do they use?
Yeah, those MHD models, I wish they were on the call because I took the data, I didn't really work on the simulations themselves, but they're pretty detailed. I know there's references for those simulations. Some of them were developed to try to replicate or predict rather, the eclipse in 2019. So I would say look up those papers, or I can post them in chat after. But those, yeah, they're MHD models.
MHD models, yeah, that's what I was after.
Yeah.
Okay, thanks.